Good day to everyone. So in this video, we are going to discuss about the determination of the surface tension and angle of contact using the Quincke's method. So this Quincke's method is actually applicable in the case of a liquid which do not wet the surface in contact with the any solid surface. For example, if you consider the mercury and the glass, the mercury will not contact with the glass surface, so that this kind of liquids, this Quincke's method is applicable to find out the surface tension as well as the angle of contact. So therefore, we shall consider the for this case, we are going to consider the mercury for which this method, this Quincke's method, is actually frequently used. So I have already mentioned in the matter of the shape of the liquid drop resting on the solid surface, which does not wet the solid surface. It is having the that is the solid surface is actually experiencing two different forces. One is the surface tension forces as well as the gravity. For example, if you consider a horizontal plate and if you pour the liquid, any liquid, means the mercury is actually, suppose you drop the mercury on it. Suppose if it's a very small drop, then it is actually having this perfect spherical shape. Suppose if you pouring the mercury a large size, so what happens is it is actually spread over this plate and making it as almost like a horizontal surface. Okay. For example, if you see this figure, this is the horizontal glass plate, and if you pour the mercury on it, that will, and in a large quantity, then it is actually making a it's actually spread over this glass surface, and the top of this mercury will having the exactly a horizontal surface. Suppose this liquid is actually very small in size, then it is actually having the perfectly a spherical shape. So once the force means so the drop is very small, then the surface tension is actually predominantly dominate the surface, and once if you pour the large quantity, then the gravity is actually dominating the surface tension, so that it is actually acting on the whole surface of this mercury. So this explains the gradual flattening of the drop as it grows in size until its top becomes quite horizontal, beyond which no more flattening occurs due to the limit imposed by the angle of contact of the liquid and the solid in this case. For example, if you consider if we put the tangent angle from here, from this contact from here, then this is a tangent, and this angle is actually known as the alpha, and this angle is actually known as the, suppose it's taken as a theta, and that is the angle of contact. So usually for the mercury, the value of alpha will be equal to 40 degrees, so that the value of theta will be equal to 140 degrees, so that the total degree is 180. The total the horizontal line is 180. So the value of alpha is equal to 40 degrees for the mercury, so that the angle of contact will be equal to 140 degrees for the glass plate as well as the contact with the mercury. So let us consider the equilibrium of this mercury drop in two different ways. One is by just involving the angle of contact, or when it is not known, and the involving the angle of contact when it is known. Okay. So first we are going to find out the surface tension without finding this angle of contact, and in another case we are actually calculating this angle of contact, and then you are actually relating this angle of contact with the surface tension. Okay. So in first case, what we are going to do is we are going to determine the surface tension of this liquid, involve, not without involving the angle of contact. So first, without involving the angle of contact. So suppose if you consider the large drop of mercury, and its central part is actually perfectly horizontal, and if you exactly separate this liquid in the half, that means if you separate this liquid by half on the left side as well as right side, suppose if you draw the vertical line and consider only one part only in the left part of this liquid, and the thin slice of this liquid drop which is actually shown by A, B, D, E, F and G is actually shown in this figure. That is the one half of the drop. Thus the obtained with the vertical faces cut parallel with each other, so that the horizontal width of GA is actually taken as B. Similarly, the FJ is also taken as a B. So the GA, that means the distance between this is actually taken as B, small b, so which is also equal to the F1 to G. So as we know that this the liquid is actually in perfectly in equilibrium state, there are two forces acting on it. The forces acting on this two sides are so there's a G, C, E and F. We have on the opposite side of this graph. So this is the one part of the liquid, and another part of the liquid is actually shown in this dashed line, that is A and this N and J, and with which are actually equal as well as the opposite in direction. And that is another another is the pressure immediately above and below the horizontal part of this horizontal part as well as the top. So now what we are going to consider is we are going to consider a small portion of the slice which is actually shown in this layer with a dashed line, which is lying above the horizontal plane of D, L, K and M. So that is actually the slice which we are considering, which is actually situated h distance from this top of this liquid, and this slice is actually exactly passing through this point D. So where this is the most protruding part of this liquid, where this where the surface is actually exactly horizontal here in this point, because it's actually having the curved surface. So once if you were it's having the maximum area at this point T, it is actually making a horizontal line. That means the surface tension is actually acting vertically upwards. Therefore, at this point of D, this slice is actually having the maximum area. That means the maximum greatest horizontal surface. So now we are going to consider what are the forces acting on this particular slice which we are considering. So one is the one force is acting on this slice is the surface tension at this point D. Let us consider this as taken as sigma here, because we are already considered the sigma is the surface tension in our previous videos. Therefore, this surface tension is actually vertically upwards and therefore there is no horizontal component is available at this point D. So only the vertical force, the vertical surface tension force is acting on it. So the another force is the hydrostatic pressure, the lateral hydrostatic pressure, which is actually facing this face of G, L, K, A due to this neighboring part of this liquid on its right side. So you have another the half of this half of the liquid is available in this right side, which is actually producing the hydrostatic pressure on this part. It's actually acting on this direction, that is acting towards the left of this liquid drop. Similarly, we have another force, that is a pull due to the surface tension over this part GA, which is actually perpendicular to this surface GA, which is actually acting on the right side, which is also as a sigma. So among these three forces, one is the surface tension which is acting upwards, and hydrostatic pressure, and another surface tension which is actually acting right side, acting right towards the right. So only we have a two horizontal forces acting on this slice on this liquid surface, which is also equal as well as the opposite in direction. So since this liquid surface is actually in equilibrium, we consider this hydrostatic pressure as well as the surface tension will be in the equal in magnitude, but in the opposite direction. So we can then determine what is the hydrostatic pressure acting on it. So the hydrostatic pressure acting on this area G, L, K, A can be given by, so the hydrostatic pressure let us take this as P over the area of G, L, K and A, which can be given by half the times of the H, that means the distance between this horizontal slice as well as the top of this liquid is taken as a H into rho into G. Here this H is the height from this the slice which we are considered from the top of the liquid. Rho is the density of the liquid, as well as G is the acceleration due to gravity. Therefore, we can find out the hydrostatic thrust, which is acting over the area of G, L and K into A, which can be given by the pressure into area. So the pressure over the area of G, L, K and A, which is actually equal to the half into h rho g multiplied by this area, which can be given by this is height as well as the breadth, so that we can write as h into b, so that I can write it as half into h squared rho g into b. So that is my hydrostatic thrust over the area of GLKA. And we have another force acting on the right side, towards the right side in the vertical perpendicular to this GA area, which is actually due to the surface tension, and this surface tension can be given by the surface tension, which can be equal to this the magnitude of the surface tension into the area, that means B. So since we already know this, these two forces are actually in opposite direction as well as the equal in magnitude, I can equate these two forces, that means the hydrostatic thrust as well as the surface tension, so that the sigma B, which will be equal to half the h squared rho g into B. So from this equation, this B and this B will get cancelled, so that sigma is equal to half into h squared rho into G. Therefore, the surface tension of this liquid can be determined. Suppose if you know the value of the h from this, the h from the experiment, and if you know the value of h and the density of the liquid is already known, then you can easily calculate the surface tension of the any liquid or a mercury in this case. So you can see from this equation, we doesn't have any the quantity or parameter which is actually including the angle of contact. So next, what we are going to do is we are actually involving the angle of contact, and we are going to find out the surface tension using this angle of contact. So the second one is involving angle of contact to find out the surface tension. So for this case, what we are going to do is we are going to consider the whole slice. That means we are actually, for the past case, we have considered only this slice we have considered. But suppose if you are actually including the you are going to including the angle of contact in this, taking the angle of contact into the account, we are going to considering the whole slice for our calculation, so that the surface tension pull at this the sigma into B due to this mercury on this glass surface at this point of E. That means this the line of contact of the EF of the glass as well as the mercury is actually acts tangentially on the slice in the direction of this ES direction. This will be the surface tension. So the surface tension is actually acting on this direction E and S, and due to this surface tension, there is another equal and opposite reaction is actually acting on this glass plate at this direction EQ. Therefore, the horizontal component of this reactional force due to this glass along this EF is actually making an angle of alpha, which is actually equal to 180 degree minus the theta. So this is the theta, that means angle of contact is actually mentioned this here from this the angle of contact which is acting from the glass plate on this mercury, that is actually taken as theta, and this part is, that means that the equivalent reactional force acting on the opposite direction, which is making an angle theta in the glass plate, which is actually equal to the 180 degree minus theta. So if I just split this force into vertical and horizontal component, and this component can be equal to this sigma times of B into cos of alpha, where this alpha is actually the supplementary of the angle of contact for the given liquid and the solid surface, which is also acting towards the right direction, towards the right. So we have another force, the pulling force due to the surface tension over the area of GA, which is also acting in the right in the direction of right towards the right, which is actually equal to sigma times of B, which is actually perpendicular to acting perpendicular to this area of GA, so that the total horizontal force acting right side is actually equal to the it can be written as sigma B into cos alpha plus the sigma into B. That means the two forces are actually acting towards the right direction due to this angle of contact as well as this surface tension acting on this so this total surface tension force is actually opposed by the hydrostatic thrust over the face of GF, J and A. That means the whole surface which we have considered, which is actually acting towards the left side. that means exactly opposite to the surface tension which we have considered now, so that I can equate these two forces, because at the perfect equilibrium of this liquid drop, both the forces acting left side as well as the right side is actually equal in magnitude, so that I can just equate these two forces. So the hydrostatic force is written as half into the H into the capital H into rho into G into the area. Area is nothing but the H into B. Here you can see this H is nothing but the distance from the height from the height of this the horizontal surface, liquid upper surface as well as the lower surface. This total height is actually taken as a H, the capital H. The small h is actually the distance from this, so half of the slice from the horizontal surface. Please note it down. Okay. So the hydrostatic thrust can be given by half into capital H square rho into G. There is nothing but the hydrostatic thrust. So that this hydrostatic thrust as well as the surface tension is actually equal in magnitude, so that I can equate these two forces. So first I can consider this the surface tension force, that means sigma into B cos alpha plus sigma B, which is actually equal to this hydrostatic thrust H squared rho into G into B. So I just forgot the B here. So I have the hydrostatic thrust is equal to the half into H square rho J into B. Or if I take the B south side in the both places, so that I will get sigma into cos alpha plus sigma, which is equal to half into H square rho G into B. So this B and this B will get cancelled, so that I can write this. So sigma into cos alpha plus sigma, which is equal to half into H square rho into G. Suppose if I just multiply this equation by 2, I will get 2 sigma of cos alpha plus 2 sigma, which is equal to H square rho into G. Or if I take this H2 sigma as outside, 2 times of sigma is taken as 1 plus cos alpha, which is equal to H square rho into G, or sigma can be given by H square rho into G divided by 2 into 1 plus cos alpha. So from this equation you can see that the surface tension of the liquid can be calculated in terms of this alpha. The alpha is nothing but the supplementary value of angle of contact, that is alpha is equal to 180 degree minus theta. So if we know the value of H and alpha from this from the experiment, you can easily calculate the surface tension here sigma. Okay, so next we are going to find out how this this small h as well as this capital H is actually going to determine using the experiment. First we are going to find out the measurement of the small h. So for measurement of this small h, the distance between the top of the drop and the horizontal surface of the maximum area, we must determine the point at this point D, that means at this point D. So where the free surface of the drop is perfectly vertical. So this has to be done by the arrangement of as shown the figure. So in order to find out the distance from this this point at this point of from D to this point, I mean the H can be calculated using the microscope setup. So this microscope is actually can be moved as a vertical as well as the horizontal direction. So in this setup, we are actually having the plain glass plate, actually which is having known as a glass plate P, which is situated as which is actually fixed with the microscope, which is having an angle of 45 degrees, which is arranged horizontally right in the front of this most protruding part of the drop, that is at the point of D. Therefore, if you eliminate the drop from using a light source through the lens, then the plate glass P will acting as a mirror on the top of the edge of the drop. When a therefore the bright and thin horizontal line will be the bright and thin horizontal line is actually seen from at this point of D. so that you can just focus this point D, and then you can measure the distance, measure the values from this vernier microscope. So the aperture of the microscope is actually adjusted until this bright horizontal line is actually coincident with the horizontal wire of the eyepiece, and its reading is actually noted. So this microscope is then which is actually capable of both moving in the vertical as well as the horizontal movement. Therefore, it is actually raised up and move towards the drop until the image is actually flat. That means you are going to place the horizontal line at this point, where this the horizontal line is actually situated in this mercury drop, and then again the readings are noted from this the vernier microscope. So the difference between the two readings is actually giving the distance from the middle point of from the point D to this the upper surface of the mercury, which is nothing but the H. Similarly, you can also easily calculate the total distance of this the angle of contact of the mercury as well as the glass, and the horizontal surface can be noted down, which is known as the H. So the capital H. So this may be easily done by means of the microscope. That means the microscope is actually focused on the top of the surface, and then the readings are noted, and then the point is actually taken to this bottom of this surface. Then again the reading is noted. Then the distance between these two actually giving the distance with the height of H. So similarly, you can also measure the angle of contact. This is the horizontal surface of the glass plate, and this is the mercury plate, the mercury liquid part. And suppose if you find out this angle of contact alpha, then you can easily find out what is the theta is. So we already have the relation of H squared rho half into H squared rho into G, which is actually equal to this H squared rho G divided by 2 times of 1 plus cos alpha. So from this you can easily calculate this H squared, which is equal to the capital H squared divided by 1 plus cos alpha, or this 1 plus cos alpha, which is actually equal to this capital H squared divided by small h squared, or this cos alpha, which can be equal to the h squared divided by small h squared minus 1. So from this relation, suppose if you know the values of capital H as well as the small h, we can easily calculate the cos alpha. From this, we can easily calculate the alpha, which is nothing but the cos inverse of h squared divided by h squared minus 1. So from this relation, you can easily calculate the angle of contact, the alpha, which is at the supplementary angle, so that you can easily calculate the angle of contact theta, which is equal to 180 degrees minus alpha. So from this relation, you can easily find out the angle of contact as well as the surface tension. Okay, so this method of calculating the surface tension as well as the angle of contact is actually known as the Quincke's method. Okay, so stop here, and if you have any doubts, then we can discuss in the online class. Okay, thank you.